This is lecture 4.1 on maximum and minimum values for Calculus 1. You might notice from the original slide that I've got a new haircut. That'll be explained later. So far we've been looking at derivatives, and besides figuring out how to calculate them, hopefully you've been learning what they actually are and what they do. And so we've learned a couple of things about a derivative. The first, hopefully, is that a derivative is the measure of instantaneous change at a specific value. So a great example of this is when you're driving your car. It's easy to calculate an average speed if you know the distance you traveled and the time you traveled. But it's not so easy to calculate the instantaneous speed at any second. We have a great tool in our car called the speedometer that gives us our instantaneous change or our speed at that second. So we can look down and see that we're going 35 or 55 or whatever. Also remember that a derivative is the slope of a tangent line to a given function's graph. Now all this means is that the derivative is the slope at a point. In algebra, we learned slopes between 2 points, which gives us average rates of change. Derivatives give us the slope at a point, or an instant rate of change. We also learned that derivatives tell us marginal functions, such as cost, revenue, or profit. And remember that marginal functions are, if we're looking at cost, it's the cost to produce the next item. If it's the marginal revenue, it's the money we will make, the revenue that will come in for selling the next item. So if we're looking at the marginal revenue at 20, this will tell us how much revenue we will earn on the 21st item. And similarly with profit. So marginal profit at 21 tells us the profit we will make on selling the 21st item. Not for selling 21 items total, but just for selling, making and selling the 21st item. Okay? So why do we care? Well, you know, in any job that you have, whether you're in healthcare or you're in business or you're in engineering, we tend to be interested in a couple of things among others. The first thing that we're interested in is how are things changing? Are things getting better or are they getting worse? Are our profits increasing? Are our profits dropping? Are our costs increasing? Are our profits dropping? Or excuse me, our costs lowering? You know, these can be very important trends. And for example, if our costs keep increasing, we want to look at that and maybe figure out a way to reduce some costs. The second thing we want to do is figure out how to optimize things. And the first one obviously plays into this. If our costs are increasing, we want to figure out what's the optimum cost or optimum cost and revenue combined together so that we optimize our profit. And all the optimization means is we want to get the best. And so sometimes the best is the lowest. For example, in terms of cost. If I have a business, the best cost for me is the lowest cost. If we're talking about revenue or profit, these things I want to maximize or make the largest. So optimizing doesn't always mean the biggest. It means, you know, it's relative to the item we're talking about. Optimizing costs means lowering them. Optimizing revenue means increasing them. And derivatives can help us do both. And it's interesting because they can do it in a fairly easy and intuitive way. So let's look at it. So again, optimization generally tends to mean that we are looking for the highs or lows of something. So you have to know the context of what you're talking about. If we think of a mountain range, it's not a tough question to point out the highs, which are the mountain peaks here pointed to by the yellow arrow, or the valleys, which are pointed to by the blue arrow. It's really easy to see, right? The high is the top of the mountain, the low is the valley and the floor. Functions are sort of like mountain ranges, and here's a graph of a function in that they may have many peaks and valleys. So here's a simple function here, and if I connect it with a line drawing or the actual functional curve, it's easier to see the peaks and valleys, similarly to the mountain range concept. So let's look at some vocabulary and some concepts. So we say a function is increasing if the y value, the functional value, remember f of x is equal to y, if it's going up. And pictorially, we see this with the mountain range, or even in the graph on the bottom left, that we are going uphill from left to right. So our y value is increasing. And so we say that in this case, that first piece, the function is increasing from 0 to whatever that first value is. I can't even read it there on the bar graph. Now notice that the slope is positive, right? Remember that we have an increasing function. When a function goes up from left to right, the slope is positive. And since the derivative is the slope at any point along here, we know that the derivative is positive. So an increasing function, a function that is increasing, has a positive derivative. A positive derivative indicates that the function is going up. Similarly, we can think of decreasing functions as going down. Notice the y value. In all of these, we're talking about the y value because the y value represents the function value. So y is getting smaller. So now between the first graph and the second graph, the first bar and the second bar, we see that the function is now decreasing. It's going down. And we can even see that intuitively with just the bar graph. We know from, let's say if this is year 1 and this is year 2, whatever this function is, it's going down. This would be good if it was a cost function. It might be bad if it's a profit function. Okay? So again, pictorially, if we use the mountain, we can see that we're going downhill now. And as we know, hopefully from algebra, that a function that goes down from left to right has a negative slope. And again, since the derivative is the slope at any point, notice the slope all along this piece of the function is going to be negative. So a decreasing function has a negative derivative, or a negative derivative indicates that the function is going down or decreasing. We say we have a local maximum, and notice here in both of these pictures, the mountain range and in the graph, we have a couple of maximum possible values, or mountains if you will. So each of these is considered a local max because we have multiple ones of them. And the local max is where the slope goes from positive to negative. And you can see that here on the mountain. It goes from yellow, positive slope, to blue, negative slope. So let's keep going on. Notice that the slope exactly at the mountain top is 0. If we're going from a positive number to a negative number, we have to cross 0. This isn't actually true, and that's why it says or it's undefined. It could be possible that we don't have a value there. We go directly from negative to, or positive to negative without touching 0, without having a 0 value. And this is when, excuse me, the derivative is undefined. Similarly, we can extrapolate about the local minimum. And this is when a slope goes from negative. You can see again here on the mountain range, it goes from negative blue to positive yellow. We can see it down here where the blue arrow is pointing. We go from a negative slope to a positive slope. So when the slope goes from negative to positive, we have a local minimum. Also notice here again at the bottom, at the actual minimum, the slope is, the derivative, excuse me, is equal either to 0 or it is undefined. Okay? Why is there no derivative on a sharp corner, but there is one on a curve? Well, a curve represents a continuous function, and that means you could draw the function without lifting your pencil off the graph. Okay? And so, since it's continuous, and if a number goes from positive to negative or negative to positive, in order to do that, it has to cross 0. Where a sharp corner can actually go directly from positive to negative without actually hitting 0. Remember back from algebra that a 0 slope means that you have a horizontal line. A horizontal line of, for example, y equals 3 or something. Or here it looks like y equals 10. Okay, the first bar graph. So here when we're going, when the slope is going positive and then it's going to start curving, getting closer and closer to 0, and then it actually becomes 0. At this top, the slope is actually 0 because the tangent line is actually horizontal, and that's the same case with the bottom curves as well, the minimum curves here, that it's going from negative and then it hits 0. So at some point along here, the tangent line becomes a horizontal line, and that's when, remember that that a slope is 0. Okay, so that wasn't actually me there, which of course you knew. This was a guy named Pierre Fermat. And he, interestingly enough, he was a French lawyer who did math as a hobby. And despite his amateur status, he was one of the two inventors of analytic geometry. Descartes was the other, another French guy, father of modern philosophy. And it's interesting because his methods for finding tangents to curves and maximum and minimum values occurred before the invention of limits and derivatives. And so they actually made him kind of the forefather of calculus, or the forerunner of Newton in the creation of differential calculus. So Fermat's theorem says if a function f has a local maximum or minimum, a mountain top or a valley floor, at some value of c, this is x equals c, and if the derivative exists there, then the derivative has to equal 0. So this is really important for us in using derivatives in functions and in business and in engineering if we're trying to optimize something. Okay, so if we have a function, if we can figure out what the derivative is and then set it equal to 0, we now know that at these points, wherever that derivative equals 0, that the original function has a local maximum or minimum. Okay, so when we set the derivative equal to 0, this is called a critical value of the function, because it's critical because it's either a maximum or minimum. We can also set the derivative, we can look for values where the derivative does not exist, and this will also be a critical value. So the critical values of a function are where the derivative equals 0 or where the derivative does not exist. And we'll look at some problems with both cases. Again, critical values are where the derivative equals 0 or where the derivative function doesn't exist. Remember back in algebra we found there were two types of functions we looked for to find values where they didn't exist. Square roots could not be negative. So if the function has a square root in it, look and see if you can put a value in under the square root sign that makes it negative, and this would be a critical value. Also, if we have a rational function or a function that's expressed as a fraction, remember the denominator of a fraction cannot be equal to 0, and so this is another place that a function would not exist. Okay, so let's do a problem. So even without a graph, we can find system optimums using what we found out, specifically the values and signs of derivatives before and after and at the optimums. So the first thing we want to do is find the optimum values. So find the derivative, set it equal to 0, see if there are values that doesn't exist, solve for that, and then find the values before and after. Are they positive, negative? This would indicate, again, it's a positive slope, negative slope, so it's a maximum, or a negative positive would indicate that it's a minimum. Okay? So again, let's go through this one step at a time. First, we need to find the derivative. This is a very simple derivative to find based upon what we've already learned in the course. So I'm not going to take time to go through this. So the derivative of the original function is x squared minus 2x minus 3. The next thing we want to do are find the critical values. Where does this equal 0? Well, this is a quadratic equation. We can either solve it by factoring or we can use the quadratic formula. So we set it equal to 0 and factor it here. The factors of this quadratic are x minus 3 and x plus 1. Again, I'm not going to go back to algebra for this. You should know how to solve this at this point. Setting each of those factors equal to 0, we get x equals 3 or x equals negative 1. So these are the two critical values of our function. So we know that at x equals 3, there's either a minimum or a maximum. We know at x equals negative 1, this is either a minimum or a maximum as well. So now we want to figure out what are they. Is that f of 3 a minimum or maximum? So what we do is we plug in values before and after 3 into our derivative to find out simply is it positive or negative. Okay? So if we plug in 2 to our function, what do we get? 2 squared is 4. Minus 2 times 2 is 4. So 4 minus 4 is 0. Minus 3 is negative 3. So before x equals 3, the derivative is negative. Let's put in 4. 4 squared is 16. Minus 2 times 4, which is 8. 16 minus 8 is 8. 8 minus 3 is 5. It's positive. So we go from negative down to positive up. Notice what we have here is a V shape. So at x equals 3, we have a minimum. Now it looks like I skipped a step here, and that is to actually find out what the optimum values, which are always the y values. We should plug these values back into the original equation to find the actual y values there. And at f equals 3, we get negative 7. All we're done, again, we're plugging these into the original equation because we want the absolute or the relative maximum or minimum, or the local. You can, relative and local are the same. We want the values of the y on this function. So we plug in 3 to the original function, we plug in negative 1 to the original function, and we get these two values. Then we check to see if they are minimum or maximum. Okay, so at x equals 3, this is just what I went through. We plug in 2 into the derivative and find out it's negative. We plugged 4 into the derivative and found that it's positive. So since the slope goes from negative to positive, we know that 3, negative 7 is a relative minimum. Now this is the point on the graph. The actual minimum value is negative 7. The x value tells you when it occurs. The y value tells you the actual minimum or maximum value. So if we do the same thing with negative 1, we plug in a value less than negative 1 here. We plugged in negative 3, a value greater than negative 1, 0, both into the derivative. And we see that the slope of the derivative goes from positive to negative, We have a mountain. So this is a maximum. Okay? So there are our answers. So again, what we're going to do is we're going to find the derivative. We're going to set that derivative equal to 0 or see if there's a place where it doesn't exist. We're going to plug those values, those critical values, back into the original equation to find the y values. And then we're going to pick values before and after the critical values, the x values, and plug them into the derivative to see that what's happening with the slope before and after, so we know if that point is a minimum or a maximum. Okay, so here's a good chance for you to do one on your own. Why don't you hit pause and see if you can do this one. Find the derivative, set it equal to 0, find the critical values, plug them into the original equation, then find out if there are minimums and maximums by finding the slope before and after the critical values. Again, another pretty simple, easy derivative to find. I'm not going to go through that. Here we have a cubic function, but notice there's an x factor in all of the terms, so we can factor out an x, and then we get a cubic function and a quadratic, which we can then factor or use the quadratic formula. So if we factor the derivative, we get x times x minus 3 or x plus 2. Notice we now have 3 critical values. We're going to plug these back into the original equation to find the y values. F of 0 gives us 8. F of 3 gives us negative 31/4. F of negative 2 gives us 8/3. It's a good idea for you to practice this arithmetic. A lot of students make foolish mistakes on doing this arithmetic. Practice is key here. Now remember what we're going to do is we're going to look for a value, derivative values before 0 and after 0, before 3 and after 3, before negative 2 and after negative 2 to find out what each of these points are. Are they maximums or minimums? So at x equals 2, when we plug this into the derivative, we go from negative to positive, so it's a minimum. At x equals 0, when we plug this in, we go from positive to negative, so this point is a maximum. At x equals 3, we go from negative to positive, and so this is a minimum. Again, I'm not going through those. You should be able to plug those in, and I highly suggest you do this just to make sure you can do the arithmetic. Take your time, because on a test you don't want to make a simple mistake like that. And there's the graph that you can see. So again, we have a minimum, then a maximum, and then another minimum, which we can see here. Alright, here's another practice problem. I suggest you try this one on your own first. This one, I think, has a little trick to it. Pause it, go through the process. Find the derivative, set the derivative equal to 0, find the y values using the original equation, then find out whether each of those points is a maximum or minimum by finding the derivative values before and after each critical value. We find the derivative here. Now, this one, unfortunately, is not an easy thing to factor. Looks like you might be able to do grouping by factoring by grouping, but when you do that, it still doesn't work out. So here's a little trick that we can use. We can figure out where the optimums exist. Remember, where this equation, the derivative equals 0. So if you plug this equation into your calculator, you should know how to do that. If not, go to Google and figure out how to type a function into your calculator and graph it. But above the graph button is a table button. And look at the table and see if you can find any x values where this whole function, or the y value, goes to 0. And if you do that, you should find out that if you plug this into your calculator and look for x's where the y is 0, you'll get two values, x equals 2 or negative 2. Remember, we plug these values back into the original equation and solve, and we get two values, negative 32/3 and positive 32/3. And again, we're going to go try to figure out whether these are maximums or minimums. So we plug a value in less than negative 2 and greater than negative 2 into the derivative. So we'll pick negative 3 and negative 1, or actually 0 would probably be easier. So at x equals negative 2, when we plug those values in, the slope of the derivative, or the slope, goes from negative to positive we have a valley, negative to positive we have a v, or a valley, so this is a minimum. At x equals 2, we have a problem here. When we plug in 1, the slope is greater than 0. When we plug in 3, the slope is also greater than 0. So the slope goes from positive to positive. Now, how is this possible? Well, what's actually happening here is a special case, and it's called a horizontal point of inflection. And this is when the slope doesn't change polarity. If it goes from negative and continues to go negative, this is called a horizontal point of inflection. And here's a picture of this graph. And so what happens is you kind of have, if we use that mountain analogy again, what you kind of have here is a ledge or a cliff. So the mountain goes up, it has a little ledge, and then it continues going up again. So if the slope goes from positive to positive, we no longer have an optimum value here. We do have a critical value here, but at this critical value, it's called a horizontal point of inflection. It's important for you to know that for the tests and for this course. All right, let's try another one. I suggest you hit pause. We've done 2 of these already, if not 3, and see if you can do this one on your own. Hint, this one has a value that doesn't exist. All right, so first we find the derivative, and notice we have a rational function. So when we have rational functions, the only way a rational function will equal 0 is if the numerator can equal 0. Since there's a constant in the numerator, we don't have any values here where the derivative will equal 0. However, if the denominator can equal 0, then the function does not exist. Remember, you cannot divide by 0. So notice that the denominator will equal 0 when the cubic root of x plus 2 is equal to 0. Well, that's going to happen when what's inside the house is equal to 0, or x equals negative 2, because negative 2 plus 2 is 0. The cubic root of 0 is 0. 3 times 0 is still 0, so we get a 0 in the denominator. Okay? So the derivative is undefined at x equals negative 2. So this is our critical value. We're going to plug this back into the formula like we've done before. When we plug this in, we get the functional value here, y equals 0, because negative 2 plus 2 is 0, raised to any power is still going to be 0. And now we want to find out, is this a minimum or maximum? We're going to do the exact same thing. We're going to look for the derivative at a value of negative 1, and we'll look for the value of the derivative at 0. And we'll see that the slope goes from negative to positive, no problem. So this is a minimum. Again, we go from negative to positive. Now, an easy way to do this, at least when you're trying to figure out if it's a minimum or maximum, is to plug your derivative into your calculator and then go to your table like we did before. Then you can easily see You don't have to keep calculating all these numbers, especially in the last problem where we had 3 values. If you put this derivative value in your calculator, you can look at the table and see what's happening before and after each of those critical values. And you should be able to see the critical values equaling 0, too. So here we have a minimum, and as we talked about before, this occurs when you have a point in a graph, not a curve. So notice we come down to a sharp curve or sharp corner or sharp point in this graph, and that's why that value does not exist. Okay, so far we've been talking about relative or local minimums and maximums, and this is the idea that a graph can have multiple minimums and maximums because of its changing slope going up to down or down to up. The absolute minimum is the lowest y value over an entire domain. Okay. So if we look back at that original chart, we could say over those 5 years, what was the absolute maximum? What was the absolute minimum? The absolute minimum would just be the lowest y value. The absolute maximum would be the highest y value. Okay? It's a very simple and very intuitive idea. So simply the highest or lowest points on the graph over a defined domain. So be careful here, because one of the things that is important here is that since I'm defining the domain, we have to look at the endpoints as well. So for, well, here I'm going to go through this example and you'll see what I mean. Okay? So notice this function, if we look at the entire domain, it has an absolute minimum. The lowest point on the graph, the lowest y value occurs down here at 3, negative 31, 4. Okay? This point is the absolute minimum. We would actually say the absolute minimum is negative. I don't know why it says negative 3/4, because that's certainly not negative 3/4. That point is marked right. Oh, 31/4. You can't see it there. Okay, negative 31/4. Remember, the y value is actually the minimum value. So the function has an absolute minimum at this point, and the absolute minimum is the y value. Okay. But notice also that this function has no absolute maximum. Why? Because the function keeps going up. Since it never stops, it goes to infinity, it has no absolute max. Now, if we change the domain and we say it's not over the entire thing, if we go from negative 2, which is here, to negative 1.8, which is here where it's crossing the x-axis, we now have to not only consider the local max and mins, which are these. This is the valley, a local min and a local max, but we also have to consider the endpoints, and this is what I was just talking about. So there's one endpoint here at negative 2, which also happens to be a local min, so that's fine because it's already included in our critical values. But notice this other value at 1.8 is not a local max or min, and we still have to consider that. So when we're looking at a function, we're not only going to find the critical values, we're also going to find the values of the function at the endpoints of the domain. Okay? So if you look at this function over that new domain, we can see that the absolute max was this point here at 0.8. But the absolute min is not at negative 2, our local min. It's actually at the endpoint, which is 1.80, because remember we're looking at the lowest y value, and this y value is lower than this one. So it's very important when you're looking for absolutes that you include the endpoints in your calculations. Find your critical values by setting the derivative equal to 0 and plug those back into the original function. But also plug the values of the endpoints into that original function. All right. In the last example, we saw that if we limited the domain of the function, we found an absolute max, even though in the entire domain, or the domain of all numbers, there wasn't one. This is a good demonstration of the extreme value theorem. The extreme value theorem says if f is continuous, which means there's no sharp points, there's only curves, and there's no holes, and it's on a closed interval, that means it has two endpoints. Infinity is not an endpoint. Infinity means it goes on forever. It's on a closed interval, which means it includes the endpoints. An open interval would mean it does not include the endpoints. Okay? If f is some function that's continuous on a closed interval between x equals a and x equals b, notice the brackets indicating that it's including these points, then the function attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d and ab. All this is saying is if we close the interval, then there has to be a maximum and minimum in that function. To find absolute mins and max, we've already done this a number of times, so let's just look at the steps here, and the only additional step is finding the values at the endpoints. So to find an absolute max and minimum value of a continuous function on a closed interval, first find the values of the function at the critical numbers. Now what are critical numbers? They're where the derivative equals 0. So you're going to have to find the derivative, set it equal to 0, and find those numbers. You plug those back into the original function. We've been doing that for this whole lecture. Next, find the values of the function at the endpoints. This is saying find f of a and f of b. And now all you do is compare them. Look at the y values. The largest one is the absolute maximum. The smallest is the absolute minimum. Okay? So we already did step 1 before in the original problems, and now we've just added another step, which is if we have endpoints, we have to consider those as potential absolute maxes and absolute mins.